All right, let's dive right into this explainer. We're going to take a cinematic tour through the high-tech, incredibly complex metropolis of modern database architecture. I mean, we all know databases store absolutely massive amounts of data, right? But how do they actually retrieve it without grinding the whole system to an absolute halt? Today, we're going to find out exactly where our data lives, and we'll explore the specialized structures that make retrieving it so lightning fast.
Now, there's this brilliant German proverb that perfectly captures the high-stakes trade-off we're looking at with database indexing. It basically translates to, if you keep things tidily ordered, you're just too lazy to go searching. And honestly, that hits a nail on the head. Maintaining perfectly ordered data costs a lot of time and computing effort up front, especially every time you write new data. But that initial effort, that is exactly what saves us from endless, exhausting searching later on when we actually need to read it. Basically, every single indexing structure we're going to look at today is this delicate, constant balancing act between read speed, write overhead, and storage space.
So, here's our game plan for today. We'll start off with secondary indexes, explore where data actually lives, expand into multiple dimensions, decipher the incredibly messy world of full-text search, and finally, climax at the in-memory database revolution.
Okay, part 1. The need for secondary indexes beyond the primary key.
So you probably know that a primary key uniquely identifies one specific row or document. It's a great main address for a record. But what happens when you need to go beyond that? Like, what if you need to search a massive data set by alternate leads? Say you want to find every single action taken by user 123, or you want to search a used car database for literally every car that happens to be read. Enter the secondary index. The crucial thing to remember here is that a secondary index does not uniquely identify a single record. Instead, think of it like a signpost. It's an additional structure derived from the primary data that maps a specific, non-unique attribute, like the color red, to a whole list of matching row identifiers. It is the absolute bread and butter of relational databases. If you've ever built a basic app and wondered, why are my search queries lagging so bad? Well, understanding this little signpost is your very first step to fixing it.
Moving on to part 2. Where does data live? The space trade-off.
We really need to look at the space trade-off that happens the exact moment an index actually finds what it's looking for. What's super interesting is that the index itself usually doesn't hold the actual data you want. Often, the secondary index only holds a reference pointer to something called a heap file. And a heap file is essentially just an unordered storage repository where the actual database rows or documents are kept in one massive central place. This approach is incredibly common, and for good reason. It prevents massive data duplication. Think about it. If you have 5 different secondary indexes, say one for car color, one for the make, one for the year, you definitely don't want 5 separate copies of the car's entire record taking up space. So each index just references a location in that central heap file.
But there's a catch. That extra hop from the index over to the heap file, that costs time, especially on reads. So database architects face a major trade-off. Heap files save a ton of space by centralizing data. But on the flip side, we have clustered indexes. A clustered index actually duplicates the real row data directly inside the index itself. MySQL's InnoDB storage engine, for example, always uses a clustered index for its primary key. Now, this drastically speeds up read times because the data is literally right there the second the index finds it. But of course, it comes at a cost. It requires extra storage space and adds a bunch of overhead on writes simply because the database now has to enforce transactional guarantees across that duplicated data.
So, what if a full clustered index is just too heavy for your system, but a heap file hop is way too slow? Well, you can use what's called a covering index, and this is just a brilliant, clever compromise. A covering index stores just a few highly selected columns directly within the index itself. This allows specific, commonly run queries to be answered using only the index. Because the index completely covers the query, the database never actually needs to visit the heap file at all.
All right, part 3, multiple columns and dimensions, expanding the search space.
Now, single-value indexes are great, but let's be real. Our real-world queries are rarely that simple. If we need to search multiple columns simultaneously, we can build a concatenated index. The database just combines several fields into one single key by literally appending one column to another. It works exactly like an old-fashioned paper phone book, assuming you still remember what those look like. Because of how it's sorted, it's absolutely brilliant for finding a last name or a very specific last name-first name combo. But here's the catch.
It is completely useless if you only know the first name. The strict order of the concatenation totally dictates how the index can be searched.
And let's see how this compounds when we hit geospatial data. Think about finding a restaurant on a map. A standard one-dimensional index, like a B-tree, completely fails here. A 1D index can give you all restaurants within a certain range of latitudes anywhere in the world, or it can give you a range of longitudes from the North Pole all the way to the South Pole, but it cannot efficiently filter both of them simultaneously.
To solve this tricky two-dimensional problem, database architects rely on specialized spatial indexes, like R-trees. An R-tree acts almost like a sweeping map radar. It allows systems like PostGIS to pinpoint complex locations in a 2D space all at once. And what's truly amazing is that this isn't just for geographic maps. An e-commerce site, for instance, could use a 3-dimensional index to search for products across red, green, and blue color ranges simultaneously. Multi-dimensional indexes narrow down complex criteria all at the same time, without having to scan and filter massive datasets over and over again.
Part 4. Full text and fuzzy search. Deciphering the smudge.
So we've built structures for exact matches and precise locations. But the real world, it's messy. It is completely filled with grammatical variations and human errors. So I have to pose this question to you. In our rigid, perfectly ordered database architecture, how do you search for a typo? If a user types handbag but accidentally misses a letter, an exact match index is going to return absolutely nothing. To handle this, full-text search engines like Lucene use fuzzy querying. They decipher this bad handwriting using a Levenstein automaton. Now, don't let that name scare you. It's essentially just an incredibly fast in-memory machine that searches for words within a specific edit distance. An edit distance of 1 simply means just one single letter has been added, removed, or replaced. So instead of looking for exact, perfect keys, the index expands the search to include synonyms, grammatical variations, and typos by scanning a specialized term dictionary to find the matching document IDs.
Finally, Part 5. The in-memory database revolution. Breaking the disk barrier. For literally decades, we just tolerated the awkwardness of magnetic disks and SSDs. We had to carefully, meticulously lay out data in B-trees or LSM trees specifically to accommodate the slow speeds and clunky block structures of disks. And we did this because disks were durable, and mostly they were cheap. But as this insight highlights, plunging RAM costs have radically shifted the entire landscape. A lot of modern datasets simply aren't that big anymore, making it totally feasible to keep the entire dataset right there in the main memory.
Now, the true kind of counterintuitive advantage of in-memory databases like VaultDB or MemSQL isn't just that they avoid reading from disk, because honestly, a disk-based OS caches things in memory anyway. The real game-changing speed comes from entirely removing the heavy CPU overhead of serializing data structures just to fit them onto a disk. In-memory databases completely avoid encoding the data into disk-friendly formats. They operate directly on fast memory pages, which just unleashes absolutely incredible processing speeds. But what if your data actually outgrows your RAM? Well, for massive scale, researchers developed something called anti-caching. In this approach, the database works almost like an inverted operating system. It holds the active indexes and all the hottest, most used data in lightning-fast memory, while quietly and efficiently paging the cold, least recently used records back down to the disk. It beautifully allows the database to support datasets way larger than available memory without bringing back all the massive overhead of a disk-centric architecture. So, as you've seen on our tour today, there is absolutely no magic, one-size-fits-all solution. Every single indexing structure we looked at, from secondary heap files to R-trees to Levenstein automatons, is a highly calculated trade-off between read speed, write overhead, and storage space. So when you sit down to design your next data-intensive application, you really have to ask yourself, what is your ultimate priority? Are you building for the blazing raw speed of memory or the unyielding rock-solid durability of the disk? Think about your access patterns and let the data itself guide your architecture.